Hello and welcome back. In this video, we'll explore how to write efficient code in Python with respect to speed. Because inevitably you will come across the argument that Python code is slow. And this is mainly because Python is an interpreted language, unlike, for example, compiled languages like C, C++, Fortran, or others. But the statement is sort of true, but it also doesn't give us the whole picture, and this is what we want to investigate in this notebook. Here we want to compare three different approaches: a pure Python implementation, an optimized version, and a just-in-time compilation, which is also possible. As an example, we will calculate the area of a circle with a given radius, with a technique called Monte Carlo integration. If you don't know what it is, don't worry, we'll cover this in a second. But the point we want to bring across is that indeed a pure Python implementation is rather slow. However, we wouldn't really want to do this. Either we will use specialized libraries to help us, or speed up the code with a package called NumPy. There are also other approaches like Cython, which stands for compiled Python, that exists to optimize Python code. And the advantage, for example, of this approach is that we can develop Python code as we normally would, and then identify which part we need to optimize, and do this with this approach. Compared to other languages, this approach has the benefit that we can make use of all the benefits of Python, and in particular increase our productivity when developing code or application, and then optimize only the specific parts that we need to optimize for speed. Experience shows that only very few functions would really benefit from such an optimization, whereas most of the code is concerned with the application infrastructure, user interaction, and so on, and there compiled code doesn't really bring any benefit. So to start with, we import our libraries that we need. We need NumPy, as always, pandas for data handling, plotting with Plotly and C1. This is sort of our boilerplate that we always import. And here we import a specialized library for compiled Python called Numba. And here we only really use the just-in-time compiler GIT. We also want to measure the speed where the Python code spends most of the time, and then we can use this with an extension called LoadX Line Profiler. So as we said before, we use the Monte Carlo integration of a circle as an example. And so what is this? One way to find an integral of a function is, as we've done in calculus, to calculate the integral and then use the borders of the integral to get the value. Of course, we can do this in several dimensions. For example, we can parameterize an integral over a circle and then do this analytically. This works in somewhat simple scenarios and even in slightly more complex scenarios, but if we have very complex functions, this will no longer work because we cannot write down the integral. One other approach is indeed to use random points, and this is why it's called Monte Carlo technique. Hence, Monte Carlo is coming from the famous casino in this town. Essentially, we throw random dots somewhere on a plane and count how many of them land inside the circle compared to outside. And of course, the more points we use, the more accurate the estimate of the area of the circle will be. So let's jump to the result first, before we look at the implementation. So imagine that we have the square here, and we throw a lot of random points in. And we designate that the point is inside the circle, that we can calculate if it's in this red area, and if it's outside the circle, calculate the blue area. And then we can compare the area inside and outside, like the blue and the red points, and this will give us an estimate of the area. This is really an example in 2 dimensions to illustrate what's going on. It becomes a lot more useful in higher dimensions. Now let's look at the implementation in pure Python first. So we define a function, area circle, give it a radius and a large number of points because we want to have a fairly accurate estimate. So we say that we are the number of points in the circle we initialize to 0. Now we have the x-coordinate and the y-coordinate of all the points, and the ones inside the circle, these are empty lists. And now we iterate using a for loop for all the points we want to have, and we pass this as an argument. So we generate a lot of random numbers. This is what the Monte Carlo technique is about. First for the x-coordinate, so between here and there, and then for the y-coordinate. And now that we have the radius, we can say if our point is inside the radius, this is really just a standard formula for the circle, we add this and append the points, and if not, we append the points outside the circle. And then the area is really, as we said, it's 2 times the radius squared, the number of points in the circle and outside the circle. So we don't really need the coordinates of the points inside and outside. We really only use that for the visualization. So the critical part is here the number of points that we generate and how many of those are inside the circle. So let's do this for a radius of 2. We let this function run, and we also have the expected area from the analytical solution here by R squared. So if we do this, the area of the circle is this, and the expected result is that, and it's a very small difference. And of course, if we have fewer points, then this would result in a larger difference, and if we have more points, that would approximate our true solution. Now we can add the points, all the points in blue and the ones that are in the circle in red, and then we can see when they are indeed in the circle compared to outside, and this is what we would expect from the area. So this is the naive implementation. Now we use the same code and strip out everything that is not related to the area, so it becomes a lot more compact. As we said before, we only need in circle, and we do this because we now want to time the function. So this is the same function as above, but we only really need to evaluate this in circle, right? So we get the same result back. And here we use the special magic function percentage time, and then this tells the Jupyter Notebook interpreter to measure the timing of it, and we use 117 milliseconds. We can also run a profiler to get a more detailed view of where the program spends most of the time. So we call this on this function, and not unexpectedly, this is really at the core of the function where we spend most of the time. Now the next step we would do is to write this in NumPy. As we said before, we wouldn't really implement this ourselves, but we would rely on NumPy. So we can already do this. We used the random number generator, but instead of the loop that we have done before, we use the random number generator to generate this for us. So we sort of offload this loop to NumPy. And then we calculate the radius, and then use this efficient statement here and look if the radius is in here, and return the area. So this is essentially the same code as above, but we make use of efficient programming, and a lot of optimizing the code is coming from thinking of how we can do this. Now once we've done this, we run the timing command again, and we see that we're down to 3.1 milliseconds. So already we improve our code from 117 to about 3 milliseconds. So this is already a huge improvement where we haven't really changed so much in our code, but we used different libraries to make it more efficient. An alternative way is to use specialized libraries that are designed to optimize code. One of these is called Number, and it works by sort of passing our code to a just-in-time compiler, JIT, that then optimizes our code. So that means that our Python code is optimized and compiled, and this compiled code is then run instead of the interpreted code in the native interpreter. So this is even faster than the NumPy version above. Of course, your mileage may vary from scenario to scenario, depending on how well our code can be optimized. But if you already have a fairly optimized code, then there is not so much to do. but in general we can gain the same or similar performance to what we would expect from a C or C++ implementation. As a rule of thumb, numerical calculations can be optimized a lot better than user interaction and so on. So we need to think how we structure our code and where we need to run the optimization. However, we also need to keep in mind that the first time we call this, the compiler needs to run, so we can only really reap the benefits on the second call. So the trick here is to add a decorator to the function we want to optimize. Remember from our discussion of decorators that these special tools allow us to modify the behavior of a function without modifying the source code of the function as well. So that means we can use exactly the same code as we have before and improve the speed by a large factor by adding this one line. That means we have all the benefits of writing pure Python codes without having to sacrifice any of the performance. And as we said before, the first time we execute this compiler needs to run, right? So this is our pure Python implementation with our own for loop, as we have done before. And this is the one that took 117 milliseconds before. So the only difference that we do now is to add this decorator that will modify this function and run it. And you can see that instead of 117 milliseconds, we run about half a millisecond.